Okay, so in that last video, we finished by talking about the limitations of the Bohr model. So now we're going to see, you know, in addition to the limitations we see specifically with this electron not falling into the nucleus, we're going to see that there's also some phenomena with electrons that can't be explained when it's just treated like a particle. So we're going to have, a kind of aha moment like we did with the photoelectric effect for light with electrons now. Okay? And so the first little aha moment here is that when we look at electrons and we shoot them at a double slit, like we did for light, what we would expect is if electrons behaved just like a particle, it'd be like we're shooting a baseball or like a huge collection of baseballs that get blasted out of a cannon at two slits, and we'd expect to have 2 points or two lines where the electrons end up hitting a wall. But if we do this, what we actually observe is that the electrons form an interference pattern, a pattern just like what we saw with light, where it's behaving like a wave. So we could just say this has, this is behaving like there we go, wave. Okay. And so we see this interference pattern, and what we can do is we can actually calculate what is the wavelength of an electron. And we can use this formula to calculate anything. And this is called the de Broglie equation or the de Broglie relation, where the wavelength for anything is given as Planck's constant. So this is our wavelength in meters. It's given by our Planck's constant divided by the mass of whatever we're looking at multiplied by its velocity. I do believe. Okay. And so this term right here, this mass and velocity, we can also summarize that as the momentum of whatever thing we're looking at. But it does depend on those two things. And so now what we're going to do is if an electron can have a wavelength, we're going to say that these electrons bound to the nucleus can be treated as what is known as a standing wave. And so let's talk about what that is. What is a standing wave? And so what it is let's imagine you have a piece of rope that you're grabbing and it's attached to a wall. So you have this piece of rope right here. A standing wave is when you're waving the rope up and down, and it basically is always your two fixed points are stationary, and then you have a manifestation of a wave. And so the first standing wave would be the one where it goes up like this, and then over time it goes down like this. But it keeps oscillating up and down, and the center point on the top of this wave is always going to be the highest or lowest point. The second standing wave is the one where you have a full wavelength happen. And I should put this as a little guy right here. And then over time, this also oscillates to have, goes like this. Okay, but the wave, like the peaks and this point right here are always fixed. So this is always stationary. That one doesn't really move. On the two sides, you do have movement, but this is always stationary. And then these points are very dynamic. And these are called standing waves because you either have some completion of a wave or half completion of a wave. Okay, so here we did like half of a completion of a wave, half a wave. Here you have a whole wave. And it's all just about this state of having like these n over 2 completions of a wave. So you could have 3/4, sorry, not 3/4. You could have 3 halves, 2 full waves, so on and so forth. But the important thing is that for a standing wave, you need some n over 2 waves, where n is some integer value. Okay? Let me make sure that's true. Pretty sure that's true. Okay? And in the case of our electron, what this is going to look like is we can imagine that circular orbit. So here's our nucleus. Here's our circular orbit. What the electron is going to do is it's going to complete some number of wavelengths over the course of that. Sorry, let me just over the course of that orbit. So it's going to do some whole number of waves. So for here, we'll restrict it to some n number of waves. I do believe the 1/2 is still a standing wave, but I think we make the distinction usually of full wavelengths. Okay? And it's not just electrons that have this state. And I just want to add one more thing. So electrons bound to the nucleus can be treated as standing wave with length equal to circumference of your orbit. So we're going to fit some n number of waves in that orbit. Okay? And so not just electrons that have this wave-like nature, all objects technically have some wave-like nature to them. And so for the electron, moving at 1.6 times 10 to the 6th meters per second, that has a wavelength of 0.73 nanometers. For a baseball, moving at 43.8 meters per second, or a 98 mile per hour fastball, which has a mass of 0.2 kilograms, and we will give this mass in kilograms, that has a wavelength of 7.6 times 10 to the negative 26 nanometers. And so I think it's pretty easy for us to see that that wavelength is so small, it's basically impossible to detect. It's happening, it's oscillating with this tiny, tiny wavelength, but it's not noticeable at all. Okay? And so this is kind of like our aha moment of electrons behaving like waves. In addition to this, and largely related to this momentum component here, we have something known as the uncertainty principle, which talks about what we can know about this wave-like electron. And what this uncertainty principle says, as attributed to Heisenberg, is that it's impossible to observe both the particle and wave natures of electrons simultaneously. So it's this Heisenberg uncertainty principle. And so in more complex, well, just in different terms, it states not possible to know position and momentum of particle at same time. And these two components, the position and the momentum, and we're going to kind of look at momentum and break it down into speed. They're complementary processes. And so what that means is that the more we know about one, the less we know about the other. And so what that means is that if we can't know both the position and speed simultaneously, we can't, exactly calculate the trajectory of an electron simultaneously. And what we could do is we could relate this once again to baseball, although this might be an overused analogy, where a classical trajectory for a baseball from the pitcher's mound to the plate is going, it's going to have a little bit of rise and then it'll drop back down from gravity. But not all pitches are always going to be a strike, and they're not always going to land in the same exact spot. What you can do is you can construct basically a probability map saying that 40% of the time, 20% of the time, the pitch lands, right in that zone. 40% of the time, it's a little bit more dispersed. 70% of the time, it's somewhere around where the catcher and the ump are. And so you can take a ton of different pitches and you can track them as they go from the pitcher's mound to the plate. And you can calculate a probability map of where you would expect the pitch to be. And this can extend to our electron where we're not going to be able to know this, because in order to know this, you have to know the position and the speed it's going. But we can have a general idea of between, from A to B, the electron is going to largely be found somewhere in this area. So we have a general idea rather than a specific idea. And so we define the probability of an electron to be found in a certain region using statistical functions known as wave functions. And these wave functions are just a collection of waves / wave equations. So we're going to take a lot of different, waves that the electron could be following. We're going to combine them all together into a wave function. So a collection of all these possible waves. When we add them together, we get a better idea of what our electron's doing in terms of, its speed, but less about position, and then vice versa. And so what we're going to see as it pertains to this distribution map is that regions in the atom with a high probability of finding electrons are going to be called our orbitals. Or another way to say this is we define our orbitals as covering areas or volumes that include the highest probability of finding your electrons. And with this wave function, this collection of wave and / waves equations, this is composed composed of coordinates in space and amplitude terms. Okay? And so this wave function is going to be the basis of our quantum mechanics as it relates to our electron. We're going to be using this wave function a lot because it contains within term for speed and a term for position and term for the wave-like nature of your electron. And with this uncertainty principle, if you look this up, you would see that the product of your uncertainty in position, x, and your uncertainty in momentum, p, is equal to, I believe it's h over 4 pi. So this has to be greater than or equal to this right here. All right. Okay. So now let's talk about this wave function. And I said that the wave function, this collection of amplitudes and coordinates in space, they help us describe the electron in an atom as a wave, and it's derived using the uncertainty principle. And a proper wave function will satisfy something known as the Schrödinger equation, where when we take that wave function, where this is a wave function, and we multiply it by something called the Hamiltonian, which is just a collection of mathematical operators, group of mathematical equations, if we do some mathematical equations on our wave function, and it's a good wave function, what it will spit out is a energy that wave function corresponds to multiplied by the wave function itself. So E is energy. And so when we use this wave function, treating the electron like a wave, and we do some math on it, we can find out what is the energy of that electron. And, these are things that we're looking at with the Bohr model. We were asking, what is the energy of an electron? And, there's a lot of different wave functions that can describe all the different energy levels of our electron. Okay? And so if we take these proper wave functions and we square them, what we'll get is a probability density to where that electron can be found, and that's what's going to give us our orbital shapes. And so when we square this wave function, what we can see is that the waves that are composed within that collection of, equations, they can cancel or they can add up, like we saw with constructive and destructive interference. Okay? Additionally, if your wave function says that there's zero amplitude, so if zero amplitude at some position, that means the wave is not, if we looked at something like this, I guess we have it off to the right as well. If you have this, if we square this, which is 0, meaning that there's no height to that curve, 0 squared is still 0. All right, so when we determine these probability densities, anywhere that you had an amplitude of 0 for your wave function, we're going to get what we call a node. And that's going to be a position where we do not expect to see the electron. And that's going to become more important as we look at higher and higher energy wave functions. Okay? But we can take this probability and we can generate something like this. So I'll kind of zoom in on this. We, treat the electron like a wave. We put in all these dots just like we did for that pitch, and we get a probability density. And this probability density, the higher you are on the curve, the more likely to find the electron there. So height is proportional to probability. Okay. And what it looks like here is that the electron seems to have its highest probability at the center of the atom, so at the nucleus. And, that is something that we said before, like, not likely to happen. It's more here that the electron is crossing nearby the nucleus. It's not being absorbed into the nucleus. And we're going to see that even though we're most likely to find it near the nucleus, there's still going to be no probability of finding it there. And instead, we're going to determine the shape of the orbital itself by considering this density as well as one more term. Okay? But we'll get there in just a second. And before we go there, what we're going to do is we're going to talk about what the wave function tells us about the electron. Okay? And so these orbitals that we can generate, this sphere for the s orbital, and the wave functions themselves describe the wave-like properties of electrons. And this is as opposed to the orbits from the Bohr model. Okay? What they do accomplish, though, is that these orbitals still retain the quantized energy of the Bohr model. So we're going to see that, as I mentioned above, good wave functions are still going to tell us the energy of a given state of the electrons. And so each of these orbitals and each of the wave functions that define these orbitals are described by 3 quantum numbers. We have the principal quantum number n, which is going to tell us about the energy of an orbital. And so this is the exact same one that we saw with the Bohr. So this is same as n for Bohr radii or orbits. Okay, we have this term that talks about the energy. We have the principal angular quantum number, which is going to tell us about the shape of the electron. We have the magnetic quantum number m sub L, which is going to tell us about the orientation in space of your orbital. And then there's a fourth quantum number, which speaks to specifically about the electron itself. And this is going to be m sub S. This is the spin of the electron. And when I say for this one and this one, when I say m sub L and m sub S, I'm just saying that those letters are in the subscript. Okay. So like I said, this ms describes the orientation of the electron in the orbital. We'll talk more about that later. And so for our lowest energy orbital, which we're going to see is the 1s orbital, for the 1s orbital, that has an n value of 1, an L value of 0, and an M sub L value of 0 as well. Okay? So these are our orbitals, describing where the electron is using a wave-like nature. And so we're going to end this lecture by just considering and kind of defining a little bit more each of these quantum numbers. This n, L, and m sub L in addition to m sub S. Okay? So n is going to describe the energy of separate orbitals as well as their size. And this is going to correlate very closely with our Bohr model. The n values are going to be integers greater than or equal to 1, just like what we saw, with our Bohr model. And what we're going to see is that these energy levels are going to be, very similar to what we saw with the Bohr model. And as you get further away from the nucleus, so going from 1s to 2s, the energy is going to get less negative, less stabilized, because the electron itself is further away and doesn't get to feel that attractive force. And so overall, we're going to say that we retain our quantized discrete energy levels from the Bohr model. Okay. And, as I mentioned, larger orbital, which means a larger n, means higher energy because it is getting less stabilization from the positive nucleus. Okay. We then have our L value, which is the angular momentum quantum number, and I said that it defines the shape of the orbital. The shapes we're going to see are going to be a sphere, a dumbbell, a clover, and then when we get to higher energy orbitals, you get something that is very strange, and so it's not easy to apply a very general term here. The allowable values for L are going to be integer values ranging from 0 to n minus 1. Okay? And so what we can say for n equals 1, you can only have L equal to 0 because that's n of 1 minus 1 equals 0, and so your values range from 0 to 0. If you have an n equal to 2, you can have an L value that goes from 0 to n minus 1 is 2 minus 1, so that's 0 to 1. And that means, these are going to be integer values as well, so that's 0 and 1. Okay? And rather than, having a number designation for n, a number designation for L, what we like to do is we like to translate these numbers, 0, 1, etc., into letters. So we have 0, 1, 2, and 3. We're going to give a letter designation for 0 of S, a P for 1, a D for 2, and an F for 3. And the shapes these correspond to are sphere. P is going to be a dumbbell. D is going to be a clover. And then F is just going to be a complex shape. So we're not going to try to assign anything to that. Okay. Then we get to M of L, or M subscript L. And like I said, this describes the orientation of an orbital in 3D space. The values for M of L are integers ranging from negative L to positive L. And so if you tabulate this, if L is 0, there's only one possible value for M of L. If L is 1, you can go anywhere from plus or minus L, from one to another. So plus or minus 1 goes from negative 1 to 0 to plus 1. Plus or minus 2 is going to give you basically from negative 2 to plus 2 is negative 2, negative 1, 0, plus 1, plus 2, which is what we see right here. And so you can take plus or minus L and then just set that up as your thing. So plus or minus 3 is anywhere from negative 3 to plus 3. Okay. And then our final one is M subscript S, which we're going to see describes the orientation of the electron or its spin. And so we'll get into that after we finish our discussion of our first 3 quantum numbers in depth. And that's going to be the subject of our next chapter. And so this electron spin is a fundamental property of an electron like its charge. So the same way that an electron has its negative charge, it also has a spin about it. And so that spin, it does spin. It can be oriented either to be spin up or spin down, and we give those values of plus 1/2 and minus 1/2. That's just how they're defined. Okay, so let's summarize these first 3 quantum numbers. We have the principal number n. We said the types of values you can see for this are integer values greater than or equal to 1. And we said that what this describes is going to be the energy of an orbital and its size. Okay, we have the angular momentum quantum number L, and these are integers that range from 0 to n minus 1. And this describes the shape of an orbital, so as either S, P, D, or F. M sub L has integers ranging from negative L to positive L. And this is going to be all about the orientation in space of that orbital. Okay? Right. So that is summarizing each of our quantum numbers. The last thing I want to talk about are what are known as shells and subshells. Okay? So a combination of these first 3 quantum numbers specifies an orbital. We saw that for 1s, that was n equals 1, excuse me, L equal to 0, M of L equal to 0. Okay? And when we're looking at this, the first digit here corresponds to N. The letter here corresponds to L. And the M of L we'll learn about in lecture on Monday. And so if we look at this collection right here, N equals 3, L equals 0, M sub L equals 0, the first number, N, is just the number we write down. So for N equals 1, we write a 1 here. For N equals 3, we write a 3 here. L of 0, if we check our table, we said that when L is 0, that is the same as the shape S. So we can write this as 3S. Okay? If we did this same treatment for 2, 1, negative 1, 2 we just write down, 1, when L equals 1, that's P, so we write this as a P, and the negative 1, we're not going to go too in-depth on, but this set of 3 quantum numbers defines a 2p orbital. Okay, but that's not the only 2p orbital. We also can have a 2p orbital that has a value of n equals 2, L equals 1, m sub L equals 0. That is 2p. We could also have a third where you have n equals 2, L equals 1, and m sub L equals positive 1. That's also 2p. And so we can make statements about, things like the 3 possible 2p orbitals, as well as those orbitals that share the same first quantum number. Okay? And we're going to see in lecture on Monday that this is, I think, probably px, this is py, this is pz. It's an arbitrary designation that they are just 3 orbitals that each are in your 3D coordinate plane. Okay. Orbitals with the same principal quantum number, the same n value, are said to be in the same electron shell. They have loosely similar values for energy, and in the case of a hydrogen electron, they have the exact same energy. So, for example, 2s and 2p are in the same shell, are the same electron shell. Okay. Orbitals with the same n and L are in the same subshell. And so all of the 2p orbitals that we talked about above are in the same subshell. So all 3 2p orbitals are same subshell. And then if they have the same n, L, m sub L, then those are distinct orbitals that exist in different regions of space. Okay? So let's look at this collection of possible quantum number values and then just talk about the shells, the subshells, so on and so forth. So we said if they have the same n value, they're in the same shell. So we have the n equals 1 shell, only has one orbital. That's a 1s orbital. The n equals 2 energy level has 2 possible types of or subshell orbitals within it. You can have the 2s and the 2p orbitals. For n equals 3, that shell can have the 3s, the 3p, and the 3d. And for n equals 4, that shell contains 4s, 4p, 4d, and 4f. And these are organized from lowest energy up top to highest energy or higher energy as you go down. Okay. Each of these designations I've underlined, these are your subshells. So this 1s is a subshell. This 2s with its 0, that's a subshell. This is a subshell. And so every line in this table is a subshell. So you have, for 3s, you have, not for 3s, for 3p, you have the 3 orientations of that are all in the same subshell. And for 3d, you have the 1, 2, 3, 4, 5 orientations that are possible. And so you're seeing it says number of orbitals in subshell. That's counting up all of these m sub L values, because you can have, for the 3D, you can have 3 for n, L of 2, m sub L of negative 2, negative 1, 0, plus 1, plus 2, but it's still always going to be 3, and it's always going to be 2. Okay? Alrighty. And so there's a couple more things I want to kind of take out of this table. And those last 2 things are that right here, where we have our subshell designation, you see that we have the F, the D, the P, and the S. This is going to tell us about the shape of that orbital. And then here, where we have the possible values of m sub L, This is telling us about the orientation. And so this has all of our principal quantum numbers. We have the n value right there in 1. We have the L value in terms of these letters, S, P, D, P, D, F. And then you have the orientation in all of your M of L values. Okay. And so what we're going to do in class on Monday is we're going to review these principal quantum numbers, and then we're going to go ahead and talk about how we actually get the shapes that we see for L. We're going to talk about how we have, why is S a sphere? Why is P a dumbbell? Why is D a clover? So on and so forth. So we're going to go from these probability density maps, basically, that are showing where the electron is likely to be. We'll talk about how quantum mechanics forbids us from having the electron at the nucleus, just like we saw with the Bohr model. And then we'll go ahead and we'll make our s orbital as this cute little sphere here. Okay, so I will see you on Monday to discuss that, and I hope you enjoy the rest of your day.